Okay, we are very happy to welcome Sergei Nechaev from Lebedev Physical Institute to give this inaugural seminar for this new year, 2021, on low-dimensional topology and non-Euclidean geometry in nature. Sergei, to you.
Thank you very much. Inaugural means that I'm the first in this year?
That is correct.
Yeah. First, I would ask you to interrupt me anytime, and I will try to go smoothly. And anyone, if you have questions, please ask me. Okay. So first, let me tell you which subject I plan to cover, and most part is about topological problems of random walks, because originally I was educated as a polymer physicist in statistical physics and disordered systems. So, and I will talk about entangled random walk and Brownian bridges, and how they are related to structure which is now more or less known in biology as crumpled globule. Okay, so then I will discuss how fractal dimension.
Recording is on.
Okay, so I can continue, I think, yeah. Fractal dimension is related to topology, and what is the interplay between them. And then step by step, I will try to cover, just to give an impression about related but different subject, how discreteness and sparseness in nature is related to hierarchy and hyperbolic geometry. So, and finally, I'm not sure that I will in time, but if I will have some time, I will try to discuss some questions related to embedding of hyperbolic tissues in 3D space, okay, and how the hierarchy emerges in this case as well. Okay, but first let us start and with entangled random walks, and let me show you just some preliminary figures. When it's possible to replace equations by figures, I will do that. Okay. So, and that is the image of the problem we were interested in many years ago, since 1985. And the question is like that. So you have in 3D or in 2D, you have three-dimensional lattice of straight roads, and inside you have a random walk which can be entangled with these roads. And then suppose that you fix ends. For instance, in two-dimensional projection is more visible. You fix ends, you don't touch anymore the ends, and you consider how many different configurations of the random walk you could have without possibility to cross these points or the roads in 3D space. So that gives you, if you would forget about these topological constraints, you will end up surely with Gaussian distribution, because all configurations are available. But when you add topological constraints, you restrict your phase space, and some configurations are prohibited. So how is possible to make any computations? What is the influence of topological constraints? So that are the questions very important for statistical physics. Okay, and it was some combinatorial approach developed by Helfen Pearson and then Michael Rubinstein in '95. So, and then with Koklov, we try to develop some analytical methods showing that this problem is related to random walks in non-Euclidean space. And that is the question which I would like to discuss right now. Okay, so now the next, what is the key difficulty? The key difficulty in topology is non-commutativity. And this can be explained by this figure. So you have the loop which winds around two roads. And typically, if you are interested in some analytical computations, so then since Edwards times, what you do, you just fix the winding number. You say how many times the random walk winds around the obstacle, around the road, and that is the topological invariant, linking number. It can be expressed in terms of Gaussian integral, and therefore some methods of path integral can be applied. But in this case, look at this shape. What you can see that you twice wind in different directions. For instance, the first road, if you will follow the path, you see that you turn first clockwise and then anti-clockwise around it. So therefore, shortly speaking, just removing this road, you will disentangle completely the full trajectory from both of them. And the same happens for the second one. If you remove the second one, so then the path can be released. One can ask how, if this is rare event or rather common, and I would say that in dense systems, this situation happens often. And for instance, the same can be shown for a situation when you have three roads. Yeah? So that this path has such shape that it is simultaneously entangled with all three roads. And if you remove at least one of them, it will be disentangled. Okay, so the shape of the path with two roads is very known in analytical geometry. It's known Pochhammer contour, and typically it's used as a contour of integration of some gamma functions and so on. Okay, now let us try to do some mathematics behind, and to do that, let us introduce, for instance, consider the situation when we have only two obstacles, 2 points, and we can introduce generators of turns around first one, clockwise or in opposite direction, or the same for the second obstacle, clockwise or anti-clockwise. Okay, so you have 4 letters, and then you have commutation relations between them. So how we can represent our contour, which we have discussed already. So it can be encoded by the word like that. So first we go, first we use a minus 1, a minus, then b plus, then a plus, then b minus. Okay, and as we know, this this path is entangled with two obstacles. Other possibility is that we exchange the letters B plus and A plus and just make a twist. And what you see that in this situation we can cancel A minus and A plus, and therefore we get 1. And in this case, the path is not entangled with these two obstacles. Yeah. So that is the difference between entangled and disentangled trajectories. And we know the group which acts behind them. This is a free group with two generators, and it can be visualized in the following way. If we have commutative structure, B commutes with A, so then we have a Cayley graph of this group in form of just ordinary square lattice, and the perimeter of this lattice at some distance from the root point grows as R, the distance from this. And if A and B do not commute, so then in this case we have some cuts. Yeah, we make cuts, and each time we generate new generation. And in this case, the perimeter grows exponentially. The perimeter is the shortest distance from the origin. Okay, so now everything is more or less, all things are known. Just few words about the metric structure of group of words. So if I have some word, so then I can make it shorter. And how I can make it? Just I look if I have the configuration when two neighboring letters are, for instance, B plus and B minus, so I can remove them and shorten the word, and the shortest possible word is the topological invariant for my path. So how it can be visualized? So first I take letter A plus, so I go this way, so then B minus, then A minus, then B plus, then I return back and cancel, and then I go this way, and the shortest distance between initial point and final point, distance from the root, is the complexity of entanglement, and the return to the origin means disentanglement. Yeah, because I cancel all possible letters, and therefore the path is disentangled. So the probability to be unknotted is the probability to return to the origin, and since I'm walking on the symmetric tree, each time I have more probability to go from the origin than to return back, and therefore if I make n steps, so the probability to come to the origin is exponentially small. Now I can reformulate this, and that is very important for topological for geometry of knots, is the following. I can consider the random walk in terms of matrices, and the simplest possible situation is when I have the 2 by 2 matrix. AK is some matrix which belongs to the group SL2R. So this is group of matrices where determinant of each matrix is equal to 1, and all coefficient modulus this relation, modulus the relation that AD minus, sorry, here is AD minus CB. Here I made a mistake. is equal to 1. So all three coefficients are independent, and then what I do, I can construct a chain or random walk or Markov chain in terms of as a product of these 2 by 2 matrices. Just I sequentially multiply them. All of them are independent, and the standard famous question and answer since 1933 is the so-called Firstenberg Theorem, which tells us how the highest eigenvalue of this chain of 2 by 2 non-commutative matrices grows. And the highest eigenvalue of this chain grows as exponentially, where n is the number of entries, and alpha is so-called Lyapunov exponent. But for us, the most important thing is that this highest eigenvalue of this chain grows exponentially, linearly, with the length of the trajectory. But now we can ask the following question. Let us consider absolutely the same problem, but we will do the following. We will add a constraint, the global constraint, that we will say, we know that multiplying all these matrices, finally, we end up with the unit matrix. So it means that we have like so-called Brownian bridge in terms of matrices. So we multiply them randomly. All of them are independent, modulus this relation that at the very end we return to the origin. So in some effective phase. Yeah. Now we can ask absolutely the same question. What is the Lyapunov exponent, say, for instance, of first half of these matrices? Because, of course, the Lyapunov exponent of all the chain is not interesting, since we return to is 0, since we return to initial point. But what is how grows the highest eigenvalue of first, for instance, half of these matrices is an important question, and the answer is like that. One can compute, one can show. First, it was done by large deviation principle, but then I will show that it's possible to compute simpler a bit. That if you add some global restriction on the whole chain and ask how the subchain grows, you will see that it grows not linearly, but sublinearly. So the highest eigenvalue of first, for instance, half matrices grows like that, when n is the number of entries. So let us note that and go further, and we will ask, for instance, the question of isometric embedding. I will repeat just known facts. So that is the Cayley. So left picture is the Cayley tree, symmetric Cayley tree with 4 branchings, and here is just the Cayley tree with 3 branchings, and this is the famous embedding of the Cayley tree in the unit Poincaré disk, unit circle. So you see that the branches become smaller and smaller till when they go closer and closer to the boundary of the disk. And another representation is so-called pseudosphere, when you make a stereographic projection of this unit disk to the Minkowski space with the Minkowski matrix. So, and hyperbolic metric in the Poincaré disk, so in this unit circle, is written here. So it's just its conformal form, and in stereographic projection you have famous representation like in polar coordinates, but instead of r square you have sin h square, so it's exponentially growing structure. Okay, so having that, yeah, so this is the something which we know from Escher books. So circle limit, so it's just another way of looking at the Cayley tree. So random walk on hyperbolic surfaces. So we have a diffusion. So this is nothing else as a diffusion equation, but diffusion equation written as in metric space where G is the metric tensor. So this is so-called Beltrami Laplace equation. If this metric, if G would be 1, would be diagonal matrix 1, 1. So then this will nothing else as just a second derivative, and you will get the diffusion equation. But if the metric tensor is like that, as in our pseudosphere in this hyperbolic space, so then one can still solve this equation, and the answer was known since many years, and that is, and as you can see, it has Gaussian part. So mu is the distance from the origin. Yeah. So this, it has Gaussian part, and it has exponential prefactor. So I will show you. Yeah. So maybe first I will return to the previous slide. So what is that? This is the probability that having a random walk of t steps, you end up at the distance mu from the origin of the hyperbolic space. Yeah, okay. So, in some specific point, if you would be interested in location of any points, to be at any points located at the distance mu, so then you should multiply by the perimeter of the hyperbolic disk. Okay, so that is like that. So you red part, red random walk is the walk which starts from the origin. So then it runs somehow and ends in some specific point at some distance from the origin. And to have a Brownian bridge, you should emit another part of such kind of random walk, which is completely independent, and then make a connection. And if you properly compute the probability of such configuration, you will see that the curvature is killed, and the probability of Brownian bridge, the probability of joint configuration of red and blue parts is Gaussian, is completely Gaussian. So therefore, I can just in words say the following. If you have the random walk which starts in hyperbolic space or on the tree from the origin, so then because the hyperbolic space has a curvature, your random walk tends to go away from the origin with a linear speed. But now let us do the following. We force our trajectory to come back at the very end, and we ask how far we are in the intermediate step. And the answer on that question is completely different. By the fact that we return at the very end to the origin, we kill the curvature, and the interior of the random walk behaves such such like it is in uncarved space. And that is just written here. The curvature is effectively killed by the condition that you force your end of the trajectory to be at the same point where you started. And I pay attention to that fact because just this fact is crucial, and as you will see in a moment, for explaining what happens with the random walks with the trivial knots in three-dimensional space. Maybe first I will make show you some picture, and then you can ask me questions if you have. So now let us go closer to polymers, and we will have an image of quasi two-dimensional representation of a polymer chain. So you can imagine that you have a random walk in a thin slit in such a way that you have no third dimension, but still you allow your trajectory to go above and below. Yeah. So the picture is like that. That is a model. So suppose that you have a carpet. Suppose that you have two-dimensional lattice, and then you have vertical strings and horizontal strings, and then you make at the boundary you close them such that this configuration produces a knot, and then you randomly distribute inside over and under crossings. So BK is +1 when you have over crossing, and -1 when you have under crossing. And the first question, just in sense of our previous discussion, is like that. What if we randomly, with probability 1/2, distribute over and under crossings? What is the typical complexity of the knot? Yeah, and of course, there is exact statement, and it's possible to make computations using algebraic invariance. So the typically knot is highly entangled, such that its complexity, I will later show how the complexity can be defined geometrically, is for instance, you can imagine that this is a minimal number of crossings which remains if you make your knot as simple as possible. Yeah. So, and typically, if you randomly generate such configuration, so then you will see that you cannot simplify essentially your knot, and the number of crossings is proportional of the number of vertices. Okay. But we can ask the different question, just in the sense of Brownian bridges, as I discussed before, in the following way. Suppose that we know that, so for instance, I am so clever that I know how to generate the unknot, and this composite blue-red curve is such that I know that it is unknotted. But still, I up modulus that I distribute randomly under and over crossings. But I generate ensemble of configurations such that they are entirely unknotted. And now what I do is the following. I make a cut, I remove the red part, and I reclose the open ends. And now I ask the question, does the remaining part remembers that it was a part of a knotted configuration or not? In other terms, the question is, if I would compute the complexity of the remaining part, could I see the difference with the situation when I just randomly generate under and over crossings for the same path? And in a moment, I will show you the answer, and it has some reminiscence with the behavior of Brownian bridges I discussed before. So, but let me for a moment stop and ask you if you have some questions.
I have a question. Could you say a little bit more about when you said the curvature is effectively killed and you can consider it a statistic same as in flat space?
What you would know more about that?
Yeah, the question is, well, I missed the point. Why is it so? You said something, but I missed the point.
Yes, right. Suppose that you have Cayley tree, yeah?
Yeah.
You have just a 4-branching Cayley tree, like, just a moment, let me show you. I have 4-branching Cayley tree, like shown on the left figure here, okay?
Yes.
So, and then I stay in some vertex, and I have the probability 1/4 to go along each branch. Okay?
Yeah.
Then I ask the question, what would be the probability to be how far I am from the origin after n step? Yeah. So, and this answer, this question is very easy to answer because I see that I have 3/4 time probability to go from the origin and only 1/4 to go back.
Right.
Therefore, I have a drift from the origin. Okay.
Mm-hmm.
So,
yes,
and it means that after n steps, I linearly in time go from the origin. So it means that the space. So another way to explain that, to say that my space has a curvature and I have a drift forced by this curvature from the origin.
Yes.
But now, when I have a Brownian bridge, what I do? I force my trajectory to make a loop and return back. Therefore, the spontaneous probability of such event is exponentially small. But now I stay in the number of configurations which belong only to this class. And consider the typical shape of these curves under the condition that I stay in the tiny region of the phase space. And if you would compute the distance in these kind of configurations, you will see that they are Gaussian.
Okay. So locally?
No, globally.
No, globally, yeah. Okay.
And this was a proof by French mathematician Bougerolles, who showed in more sophisticated terms, also using large deviation principle, so that in fact the probability, if you have Poincaré disk, two-dimensional hyperbolic surface, so then the probability to come back. Okay, so better to say, let us say about the trees, because it's more visible. So the probability to have a Brownian bridge on the tree is isomorphic to the probability of have random walk in the three-dimensional Euclidean plane. Why three-dimensional but not two-dimensional? This depends on the fact what is the probability of coming back. So this depends on the boundary conditions. Here I have some reference later on visual work, or if you can send me email.
Okay, thank you. Sorry, thank you.
Yeah. So, but the main point is that there is in Euclidean space there is no such drastic difference between open and closed trajectories in the sense of the dimension, because open trajectories go like square root of n, and closed also. The coefficients are different, but the behavior is the scaling behavior is the same. But if you are staying in hyperbolic space, this difference becomes crucial, and open trajectories deal nothing with the trajectories which are closed. So that's the point. Yeah. Oh,
I have a very basic question before you proceed. It's very interesting. I don't see. I'm sorry, I'm not familiar with this work. And question is, where do I see the constraints of topology here?
Good. Right. Yes. I would answer on this question. So, as you see, I started with okay. So, with the model like that, and here, what you can see is the true topology. Yes, because there are topological constraints created by the fact that the chain cannot go through the loop. But now the way of thinking is like that. You can do the following. Maybe I will explain this in geometrical terms, but then I think they are more clear. Let's do the following. Let's consider the elementary cell of the two-dimensional lattice. Yes? The square. And then you can tessellate your plane by the elementary plaquettes in form of squares. And now you do the following. You make a conformal transform of this elementary plaquette to the rectangular with zero angles. If you would stay on triangular lattice, then you will get an image. I will just show. You will get an image exactly like that, like here. So suppose that you have triangular lattice. So then what you have here is the image under the conformal transform of your elementary plaquette.
Okay.
What you can do, you can simultaneously make reflections of your elementary plaquette in normal space and in the, so this is called covering space. Yeah?
Sure.
And what you will see that by this tessellation in normal space, you will get just some repetitions, sometimes you will get loops, but here you will never get loops. You will because of structure of this domain, its topology is scaly. is like of Cayley tree, but this is just geometry. But what is possible to do is the following. So this conformal transform is known. We know that Laplacian operator is conformally invariant. So it's under the conformal transformation is Laplacian again. And so therefore we can consider the random walk simultaneously in initial space and in this covering space. And in addition, what we can show, and this is just what I try to figure out, is that, of course, this topological space is not directly related to the initial plane, because, as I said, in the initial plane we could have loops. Here we haven't. But if we consider the random walk in this covering space, which ends at the point when it started, so then so this is exact. This is theorem. This probability is exactly the probability to be unentangled in initial state.
That's clear. Thank you. Yeah. I understand now. Thank you.
Yeah. In another. Yeah. So maybe. Yeah. Okay. So now just coming back to this. Yeah. Let me repeat briefly again. So what we have unknot. We cut part of it and we reclose ends and we look for its complexity. And we compare this with a situation when we randomly generate distributed under and over crossings without paying attention to the fact that we don't know whether it was part of unknotted or not. We don't care. So we compare these two situations. Now, just some example. So this is unknot, and how I can simplify it. So I can remove parts, these parts. So then I can remove this one. Then I can shorten some parts. And what remains is the minimal number of crossings. And this number of crossings can be considered as a topological invariant. So, and the same quantity can be considered as a complexity for conditioned configuration as well. Yeah. Okay. So now, what is the result? If we just have a random over-under crossings without any conditions, so then knot complexity is proportional to the number of to the lattice, so just to the size of the lattice. But if we do as I said like that, so we cut part and we considered the rest under the condition that the parent was unknotted, then we immediately come to the situation that typical the conditional conditional complexity behaves not as size of the lattice but as square root of it, and this should remind us the same situation as it happens in Brownian bridges on matrices. Do you remember I told you that when you multiply sequentially matrices and we look for the highest eigenvalue, so then it grows exponentially, and in the exponent we have linear dependence on the length. And but if we make a condition, add a condition that we force trajectory to be entirely unknotted and look for the part of it, so then the what we have in the exponent behaves as square root of n. And here is the same, and that is these two answers are related to each other. And the relative complexity of a daughter node tends to 0. Yes, because you just divide square root of n by n and look for the limit n goes to infinity. So therefore, the answer, just based on these ideas and two-dimensional projections, whenever you take a knot and then you cut part of it and look for the complexity of remaining parts, and all parts are weakly knotted. Of course, they are slightly knotted because of the boundary conditions, because you cannot make, you can not ensure that the remaining part is completely unknotted, because you close the ends and you change the topology. But typically, if you ask the typical topology, it's like that. So we have checked this in real computations, and in the paper of 2014, we did the following. We generated, we took some finite volume and generated the random walk with self-intersections, the unknotted random walk with self-intersections in this volume. Yeah, and then we colored some part where of some we take some subchain such that the initial and final point of this subchain are close to each other in the space. Yeah, so any subchain, and we computed the Alexander polynomial of this subchain under the condition that the entire configuration is unknotted. So, and we have reproduced the result that so you take red parts of different sizes, and all of them are much weakly knotted. Then it would be just the random configuration, like just you take you just generate a random walk with volume interactions inside the box. You close randomly ends into you compute it. It's knotting. So now the question which we have is the following: how densely fill the space by linear chains such that every subchain is almost unknotted? There are two options. So I have dense configuration, and I have two subloops, red and green. And one possibility is that green deeply penetrates in red, so they cover the whole space, and they are they are entangled. And in this case, it's difficult to imagine that it's difficult to imagine that how it could happen that you can take different parts, and on all scales this green part is weakly entangled with the red one. Yeah. Another option is like that on all scales the trajectories are compact, I would say, in itself. So the monomers neighboring along the chain are mostly neighboring in space. So they form hierarchical structure, which is can be imagined like that. You have a long chain, and then it makes some folds. So, and then it makes folds of folds, and then it makes folds of folds of folds, and finally what it has crumples which are on all possible scales, and you imagine such kind of configuration, then it's much easier to see that on all scales there is sort of repetition of structure, and there is a possibility for chain to be weakly knotted on all possible scales. And in 98, 99, the group of Lieberman, Aiden, and other, Leonid Mirny, Job Decker, and biophysical group working on DNAs have shown that this is the result of computer simulation. They did the following. So that is the typical unknotted configuration of long polymer. Why it has such color? So they did the following. So schematically, I just say how it looks like schematically. So they take small box, they put inside very long loop with volume interactions, such it cannot change its topology, unknotted loop, and then they start shaking this, and finally they get sort of equilibrium configuration, and that is the typical snapshot of this equilibrium configuration. What means the color? What mean the colors? They have painted the trajectory from one end to another one in continuously changing color. So this figure shows you how colors are distributed in space. You see that they form domains. It means that nearest neighboring along the chain monomers stay close to each other in space. So it's just exactly as I showed you on the previous slide, this schematic formation of structures on different scales. But this deals nothing with the specific folding. They just fixed the topology, the entire topology, unknotted topology, and then they just used the Monte Carlo computations, and shaking very long time obtained the more or less equilibrium configuration of this chain. And it has such structure, and in fact the fractal dimension of this structure is 3. It's exactly equal to the fractal dimension of the space where the chain is embedded. So, and from biological point of view, so this structure is known under the names of crumpled or fractal globule, and it has very important applications in DNAs because using this structure is possible to answer the question. Okay, again, I simplified the situation, but just the idea. How one can read the information from DNA, knowing that it's very, very dense and encapsulated in very small domain. For instance, the DNA of human is of order of 2 meters and is embedded in the nuclei of size of 20 nanometers. So there is a question how to read the information from it, because you should disentangle some part, then the information should be then you should read the information from it to copy, yeah, and then you should fold again. But looking at this structure, you see that it's very easy to pull out any part of it, because on all scales they are not entangled. And now there is just very deep and big activity on this subject in biophysics, in genomics, and people are able to compute. So this is MIT Harvard group, where they learned. So they started that. They know how to compute so-called contact maps. So you freeze by special methods the structure of DNA in chromosomes, and then you can see which are the contacts. So they compute the so-called contact map. They can see which part of DNA are in contact in space with other parts of DNA. So, and using these contact maps, one can make a judgment about the fractal dimension of the whole configuration. So, and this is how it looks like. So, schematically, it looks like a piano curve. Okay, so this is the one side. So I said that unknotted chain has a fractal dimension 3, but we know that it's very hard to, if we would like to compute anything analytically, it's very hard to make that, because there is no, so algebraic invariance is very involved tool, so some topological field theory, so it's hard to use in dense systems. So there is a question whether it's possible to do anything analytically. So therefore, there is the idea which can be formulated like that. We know, okay, not know, at least we believe that the collapsed unknotted polymer loop in 3D space, typically they have crumpled structure with fractal dimension 3. So as I showed you, yes, on all scales they are knotted. But whether it's true or not that if we will generate somehow the polymer configuration with a fractal dimension more than 2 is the random walk in 3D space, these trajectories will be less knotted than ordinary globular chains. Okay, so now why this is important? One can formulate a proposal so that instead of working with true topology in very dense polymer systems, let us mimic the unknotted chains just by saying that their fractal dimension is close to fractal dimension of the space. And so then, of course, we lose all information about topology, but still we mimic somehow the structure. So that is the idea. And now in the work which is shown here, it will just appear in macromolecules. We try to show whether it's true or not, and I will maybe skip points just how we have generated this. This is also an interesting question, but let me skip it. Just showing the result. So we have generated by using special hierarchical potential the configuration of the random walk with volume interactions in 3-dimensional space with the fractal dimension between 3 and 2. 2 is the typical random walk, and 3 is this crumpled random walk, hierarchical on all scales. And here you can see the result. So when you approach when you are closer and closer to fractal dimension 3, you see that you can see more and more pronounced territories. So the configurations when close along the chain parts are close in space as well. And when the fractal dimension is like in a random walk, so then or close to it, then you lose this structure, and you see that the different parts are mixed. So, and simultaneously we have computed the distribution of knots, and here is again the same consistent with this picture result. Black shape is the typical configurations with the fractal dimensions close to 2, and as far as you make the fractal dimension closer and closer to 3, you see sharper and sharper distribution of knots concentrated on rather simple knots. So we expect that this is rather convincing to judge that there is bijection between. Okay, so mathematicians would, of course, not believe ours, but I would say, since I'm a physicist, I'm allowed to say that there is at least one-to-one correspondence between fractal dimension and topology for densely packed polymer configurations, in the sense that as weaker is entangled polymer chain, as closer the fractal dimension is to 3. So therefore one can use different tools to generate polymers with specific fractal dimension, and we believe that this will enable us or other researchers to simulate unentangled trajectories and to work with them. Okay, so I have run out of time, but let me just briefly, if you allow me, I will definitely not touch the last subject, but just me tell you about few things concerning sparseness and discreteness in nature, because this is related to another interesting topic of number theory in nature related to hyperbolic geometry. And so in many papers you can see such in many papers devoted to investigation of spectral properties of networks, of sparse networks, you can see the pictures like that. So as I said, so we have not only we, but many people, and we also have analyzed the structure of contact maps of chromosomes. And this is a typical sample of this contact map. The only thing which I would like to to show you is that this map is rather sparse, in the sense that each black point is the contact associated with some domain of chromosome, and white pixel means that there is no contact. So you see that in some resolution, this is big resolution, and the matrix looks rather sparse. So if you will compute its eigenvalues, it will behave like that, something like shown here. So then you can see the work the authors are written here. Spectral statistics of protein-protein interaction network. You will see again such peaked structure, and you can see also the distribution of ratios, some statistics of reads in some cancer genome. You see also the spectra like that, and in all situations you see that there is some hierarchy. Yes, again you see peaks, so then these peaks are separated by smaller peaks, and smaller peaks by smaller again, and so on. And what we have done the following. We have taken large matrix, rather sparse. So this is matrix of 0 and 1s, and it's matrix generated at the percolation threshold. So the probability of having 1 in this big matrix is of order of 1 over n, when n is the size of the matrix. If you increase the number, so this here you can see different graphs associated with. You can replace the adjacency matrix by the configuration of graphs. Here are different samples, typical samples. But if you will compute the spectrum of this matrix, you will see that it has precisely hierarchical structure, which is very, very stable. So again, you have random matrix. You have generated different realizations with fixed probability, and then you compute the spectral density, so the distribution of eigenvalues, and you see the structure which is like that. Here it's even better seen. Yeah. So you see hierarchy of peaks, and they are separated by smaller ones, then by smaller ones again, and so on and so forth. Let me skip some part, and so we have worked on that, and why I mentioned this, because this is just the manifestation of non-Euclidean geometry in this structure is related to some known function. So this function has so-called modular properties, discrete symmetries of special group SL to Z, which is some discrete symmetries of group of motion of two-dimensional hyperbolic space. And maybe just briefly, I'll mention that, saying the following: if you will analyze which clusters appear in this ensemble of sparse networks, so you can see that there are many linear chains, linear-like chains, and there is some finite, and there is a fraction of tree-like structures. But it's possible to show just by exact analytic computations that the 95% of subgraphs in very sparse regimes are linear chains. Yeah, and only 5% of graphs have this tree-like structure. So therefore, as a model, of course, it's not exact, but as a model, one can consider just the fraction of linear chains and ask whether maybe if we take the fraction of linear chains, maybe there we can still see such behavior, such fractal structure. And the answer is yes. And the model is the following: you take square matrix, and you take x are 1 or 0. X are random variables which can take the probability p and could be either 1 or 0. Yeah, and here is the example of just the snapshot of two typical spectral densities at different p's, at 0.5 at 0.9. Yeah. So you see that it's exactly this fractal. It has exactly such fractal structure. And what is interesting is that, so let us look at the main series. So the set of peaks which go to the sequentially go to the end of this line. Yeah. So so if you will compute the positions, they stay at any density at positions like shown here. Yes. So it's for us, for when we have seen this for the first time, it was just sort of mystery. But then we realized that this is not a mystery, and this is a fact, and it's possible to compute independently positions of main peaks and their heights. And basically, it happened that everything is related to, and that is the relation to hyperbolic geometry, to summation of Faraday numbers. So what is the similarity between these two pictures? So this is the famous port construction. So which goes like that. You take the interval between 0 and 1, and you take two circles which touch each other and touch the interval at the terminal points. Yeah, and then you inscribe the circle which touches these two and the segment. And you ask where is the position of its center. Of course, by symmetry is 1/2. But now you inscribe the third one, which is say 0.5, and you ask where its position, and so on and so forth. And the answer is nice. In order to have the position of the center, you should do the following. You should take two nearest neighbors, 1/2 and 1/1, and then sum the numerators and denominators like that. So, and you get 2/3, and that is the answer. And 2/3 you should understand as a real fraction. Yeah, and this works. For instance, if you take this small one, 0.8, so then in order to get its position, you should take 1/3 plus 1/2, you sum 1 plus 1, and you sum 3 plus 2, and you get 2/5. Yeah. And this is related just to reflections in hyperbolic geometry. This is nothing else as just the sequential reflections of triangle with zero angles, and these numbers, which are exactly the same numbers as here, are the positions of corners of these under succession of the reflections. So anyway, fourth construction, discrete symmetries of hyperbolic domain and positions of peaks in random sparse ensemble are the same. And I will show you just the example. So this is the computation using Monte Carlo method of the spectral density. This is precisely what we have done here. As shown here, just the half of it to save the space. Yeah, this is the numeric summation of the series, which can be constructed to compute this Monte Carlo to compute the spectral density. And then finally, by blue line, we have shown the analytic expression using which involves some famous function which is known as Dedekind eta function, and as you see, everything is identical. So I could say that this complex structure of the spectrum can be exactly computed in terms of some analytic function which is known in different areas in analytic geometry and so on, and it's defined like that. So it has so-called modular symmetry, and its form is shown here. So probably I will stop at that point, because I have some next slide which shows you that there is something behind this and relates hyperbolic geometry with number theory, in the sense that so you know the question of phyllotaxis. So why, if you take pines, for instance, or ananas, and you compute how many spirals you have on one fruit, so then you will get the Fibonacci number. And it was a proposition by Levitov, very nice construction, who showed that there is sort of energetic approach to phyllotaxis, and his model was like that. He took the cylinder, a finite cylinder, he distributed points on it which are repulsive. And then, since are repulsive, since the cylinder is finite, so they form the lattice. And then what you do, you just compress the cylinder, and these points, because they can move on the surface, they rearrange in such a way that they form another lattice, which has less energy. So, and if you do sequentially, you sequentially make such compressions, there is a discrete jumps from different symmetries, and this sequence is given by Fibonacci numbers, and finally it converges to golden mean. and it's possible to show that in fact you pass through the barriers, which are exactly the same structure as shown here, and everything is governed again by these discrete symmetries of by this. So you are working in this relief given by this Dedekind function, and so from this point of view, I would say that there is no mystery. You just compute the you just solve the optimization problem, and in such a way that you are trying to work in the relief under the condition that you have a minimal potential. Okay, so I would stop on that. Maybe let me show you just the team, our team, and here we are. So our team in field of polymer topology. So these are persons which I would like to mention. So we are working all together, and our friends and colleagues from United States are shown here also. So, and they are the key persons in this crumpled globule structure formation. So, and this is just my favorite picture, which shows you, maybe just by some sort of analogy, here is the coral from the sea, and this is the relief of this, my favorite Dedekind eta function, and maybe it's not, but I see the similarities between these two structures, and this forces us to, this motivates us to think more about the manifestation of some hierarchical properties of analytic functions and hierarchy in nature. Okay, so thank you very much.
Thank you very much. Thank you, Sergei. Wonderful, wonderful talk, combining so many interesting ideas from yes, many areas of mathematics.
I will show you something which maybe, of course, now it's impossible to say, as I said. So it was a conference on turbulence.
Yes.
And I should maybe it's already shown, but it was a conference on turbulence a few years ago. So, and then my friend made a picture of this turbulent flow, and then I realized that something goes wrong, because so I make magnification, and then I see that so probably it's not like just real turbulence. And I asked him. Finally, he said, "Okay, yes, I made a picture of this leaf in order to mimic the turbulence." So, and then my wife said, "Okay, so why this but not this? This is so-called jupa godet." Yes, and when this is just the how you can create by hands the hyperbolic space. Yes, just like that. So this is what my son has done.
Yeah. Thank you. Well, first of all, very interesting. I have a comment maybe to offer, but first of all, I'd like to hear any questions from the attendees, please. Well, yes. If there are no questions, I have. I'd like to point out something that is intriguing, maybe is a suggestion to explore. And when you discussed the case of a fractal dimension that was, say, above 2.
Yes.
And I thought of going towards the limit of 3. So from 2 towards 3, that suggests an interesting fact. I'd just like to point out there is a paper by Eleni Panagiotou and Lou Kaufman talking about not polynomials, but considering first the fact that you may get to these polynomial invariants by considering open curves that are getting closer and closer to a closed curve, so to form knots.
Right.
And they show, I find it extremely interesting. They show that even this is rooted as of course Ken Millett knows, is rooted in Eleni's work on linking number, Gauss linking number, showing that even for a linking number, if you consider the same situation, there is a continuous way to get to the invariant by approaching the end points of these open curves as the end points approach to form a knot. So I wonder if there is an interesting fact here, that I wonder if this situation, when you go from fractal dimension 2 in the limit to 3, you recover the same situation. You get very close to the knotting situation, and that's why you can mimic one with the other.
You know that, in fact, when we have generated the curves with fractal dimension 3, we didn't, so we can generate both closed and open. And if we are in the interior of the random walk, I should look more carefully, but it seems to me that there is no huge difference whether the ends are open or closed.
I believe that. Absolutely. Yeah. Very
And
interesting.
if you can send me the reference on the work you mentioned, I would be pleased to see it.
Sure. I'm happy to advertise this to everybody because I find it a extremely interesting paper. Is a Proceedings Royal Society that paper that appeared last year. So it's a pretty new work. Yes.
Okay. Mm-hmm. Okay.